it's not quite full screen, but sometimes this is all what you can get. So
yeah, so actually this is because of the particular program I'm using.
Yeah.
May I start?
Yeah, you can start now, please.
Okay. So first, I'd like to thank the organizers of the nice event, and yeah, I'm very happy to present at HomePath. And today I'm going to talk about consistent error bounds and convergence rates. And this is a joint work with my colleague Tianxiang Liu from the Tokyo Institute of Technology. Okay, so in this talk, our main object of interest is the convex feasibility problem. So we have a collection of M closed convex sets, and we want to find some point in their intersection. Now, there are many methods for solving them. For example, you have the mean projection algorithm, where at each iteration you update by computing the projection with respect to each set and then averaging them. You have the cyclic projection algorithm, where at each iteration you select a different set to project, and many others. So for example, you can see this very nice survey and learn many things about them. Now, and here's an example of cyclic projection. I have the impression that everybody in this audience knows about this, but no matter if you're using cyclic projection or mean projection or something fancier, there are, I guess, two questions that are very basic that we should ask about them. So first is, do these methods always converge? And it turns out, if your method is not very strange, it's not doing too many strange things, you are ensured to converge because of convexity. So that is more or less what happens in general. However, if you want to know how fast does these methods actually converge, then typically the answer will not come from convexity alone. And it will depend on the kind of error bound that holds between these sets. Now, here's a very typical kind of error bound. So now I'm just for simplicity, I'm talking about two sets. And I say that they satisfy a Holderian error bound if there is some exponent gamma, such that for every bounded set restricted to that bounded set, I can upper bound the distance to the intersection by some constant times the maximum of the individual distances to the power this exponent. And here I'm going to only deal with uniform Holderian error bounds, so meaning that we can use the same exponent for all bounded sets. And in particular, if we have gamma equal 1, this is what's called a Lipschitzian error bound. Now, the typical pattern is more or less like this. So if you have two sets and you have a Lipschitzian error bound between them, if your method is not too strange, you are ensured to have linear convergence. So your convergence will be something like this. So at each iteration, we'll be able to reduce the distance to the intersection by something like this. And if you have a Holderian error bound, typically you have a sublinear convergence depending on gamma. And this alpha will be exponent that will depend on this gamma here. Now, the analysis for the Lipschitzian case is very classic. So this is known, I think, since many decades ago. But actually, the analysis under Holderian error bounds in general circumstances is quite recent. And there's a very nice paper by Bowline, Kuhn, Lee, and Tam, where they analyze this and prove these kind of results for actually in a context more general than what I'm describing here. Now, this discussion, however, is only focused on Holderian error bounds. But in reality, not all error bounds that appear in nature, in a sense, are Holderian. So working with Scott and Tin-K Pong, we found out that if you have something called an exponential cone, so here the precise definition of exponential cone is not that important, although you know about this, so Scott's talk, but here the precise definition is not important. The important thing I want to tell you is that if you have something called the exponential cone, and you intersect it with a special subspace, you get a kind of error bound that is expressed not in this shape, but something that depends on the entropy function for small t. And if you select another subspace, the error bound will be something that depends on a logarithmic term. So these two are not Holderian in this sense, and they cannot be analyzed directly with this kind of tool. So this is one of the motivations for trying to develop a framework to encompass as many error bounds as possible, and also to prove convergence rates about them. And one thing I should mention is that this comes from the theory of facial residual functions that also appear in Scott's talk. And the framework I'm going to explain now is also able to express the error bounds that comes from this theory of facial residual function. If you want to know more details, please check our preprint. But this is a new definition we introduced in this paper. It's the definition of consistent error bound functions. So suppose we have M sets, and we denote by C their intersection. And a consistent error bound function is a function that has two parameters. Essentially, what it does is this: it receives the maximum of the individual distances and the norm of the element, and outputs a valid upper bound to the distance to the intersection. So this is the key property. The other two properties, they are important, but they are here for some technical reasons. So for example, you want that if the distance to each individual set is 0, you want this to be 0, because if the distance to the individual sets is 0, then you are already in the intersection. And you like this to be monotone. So if the points are farther, you would like this to be so if this is closer, you don't want this function to output a larger value. And we're going to call these functions strict if with respect the first parameter, when we fix the second parameter, if the resulting function is strict. And a curious fact is that as long as your intersection is not empty, you are ensured that there exists at least one strict consistent error bound function for your sets. So in principle, no matter how strange your intersection is, you can always find at least one strict consistent error bound function for your pair of sets. Now, what kind of error bounds are covered by this? In fact, if your set satisfy a uniform Holderian error bound with exponent gamma, then you can show that a function of this form will be a consistent error bound function for your sets. And the two strange error bounds I showed you can also be expressed in this framework. As well, the error bounds coming from the theory of amenable cones and facial residual functions. And although I only mentioned the uniform case here, just as a very quick side note, it's also possible to express Holderian error bounds that are not uniform using this framework. Now, as I mentioned in the beginning, the main point of one of the main points for studying this error-bound stuff is that we are interested in analyzing convergence rate for algorithms. So next, what I'd like to talk a bit about is how can we use this framework to study convergence rate properties of certain algorithms. And just a quick reminder, the reason we care about this stuff is that they provide information on how fast your algorithms are. And so we are going to make some assumptions. So we suppose that xk is a sequence generated by some algorithm to solve this problem. And what we're going to assume is these two conditions, I think they are relatively standard. First is the phasor monotonicity. At each iteration, you're not getting farther from the set. And so that at every L iteration, you get a bit of decrease. So we do not require that at each iteration, we have some improvement, but there should be at least one integer such that at every L iterations, we get some improvement. So under these two conditions, there are actually quite a few algorithms you can cover. So all the classic ones are covered under these. All the classic ones satisfy these two conditions. So mean projection, cyclic projection, maximum distance projection. So adaptive versions of this, and so on. Now I'm going to show the main convergence result. What happens is this. We have M closed convex sets, C is their intersection. We have phi a strict consistent error-bound function, and we have a sequence that we assume satisfy these two assumptions. So we construct some auxiliary function. Take the square root inside, take the power to inside. We construct some very complicated integral, and this is some special kind of generalized inverse. Some generalized inverse. And it turns out if you succeed in computing this thing, you can use the inverse of this to say something about the convergence rate. So you need to compute this integral, you need to inverse this, and after you inverse this, you can show that the convergence of xk should be either finite or should decrease using this rule. So this is not easy to compute in general, but if you manage to compute this, you get an expression that describes the convergence rate. And there's no recursion here. So this is just a formula. So you can indeed get a convergence rate from this. Now, as I hinted, this looks very hard to compute. So a very natural question is how practical is it from an analysis perspective to actually use this kind of tool. Now, so with respect to that, I have a few good news. So the first good news is that if your error bound is a Holderian one, then this thing actually has a closed form, and using this closed form, you can recover and also prove a few new results about some methods. So you can recover some of the results that were described by Baldwin, Lee, and Tom, and also prove a few new ones. Now, if your error bound is not Holderian, there is still hope to use this kind of tool using something called a regular variation. So I got the impression that regular variation is not a tool very used in optimization. I might be wrong, but this appears a lot in the literature, in the probability literature. So, and you can find more about this in these two books. And you see that these people are all people that have work on probability theory, and where it is used to analyze things when you want to understand the asymptotic behavior of function. But this definition of regular variation is relatively simple. We say that the function is regular varying at 0 if this quotient has this value, if there is some index hole, such that for every positive lambda, the limit of this quotient is lambda to the power 4. And it turns out that almost all error-bound functions we find in nature, in a sense, they are functions of regular variation. So if you have a Holderian error-bound, then this has index, this is a function of regular variation at 0 of index alpha. The entropic error-bound that I mentioned that has to do with this is actually a function of regular variation of index 1. And the logarithmic error-bound is a function of regular variation of index 0. And as I mentioned, so this first one is one where we can compute that integral. We have closed form for it. But for these last two, it's very hard to compute the closed form. So for example, for the entropic error-bound, it seems to require the Lambert W function. I think the only person that can do this is Scott. But yeah, but if you use this regular variation, if you do this regular variation stuff, you can prove some results while sidestepping the computation of this integral. And I'm going to show some of the things we are able to show. So essentially, if your function is regular variation, is of regular variation at 0 if index whole, if the index is between 0 and 1, we have upper bounds to this, to the very complicated integral that appear based on the exponent. And if your index is 0, then we actually get some lower bounds. Now I'm going to show what are some consequences of this for the convergence rate of algorithm. So if your error bound has index 1, in a sense, the convergence rate is almost linear, because this means that your function, your algorithm is converging faster than any sublinear rate. We don't know whether it's linear or not, but we know that at least it's faster than any sublinear rate. And for indexes between 0 and 1, it behaves almost the same as a Holderian error bound with exponent whole. And if the index is 0, this quantity goes to 0, is lower than any sublinear rate. And one thing I did not mention is that under very reasonable assumptions, you can show that if your error-bound function, if your consistent error-bound function is of regular variation, the index must be between 0 and 1. And for the two error bounds that I mentioned, the entropic one and the logarithmic one, using these tools, you can prove the following. For the entropic error bound, the convergence is almost linear in the sense that this is going to be faster than any sublinear rate. But you can also show that the rate is not, you can also show that this quantity here is not, you can show that this quantity here is slower than any linear rate. Now, the thing is that this is only an upper bound to the convergence rate. So a lower bound to an upper bound is not necessarily a lower bound to the convergence rate. So there is some gap here. So to examine this, we did some quick numerical experiments. So we consider the behavior of the cyclic projection algorithm applied to this problem. So we have the intersection of the exponential cone with the subspace, and the underlying error bound here is the entropic error bound. So when you take a look at the log-log plot, you see that it's something like this. So this is faster. So empirically, it seems that it's faster than sublinear, because if it were sublinear, it should appear as a line here. Now, when we take a look at the plot where only the y-axis is in log scale, it looks something like this. So it's some indication that it's not, it doesn't have linear convergence, because if it had linear convergence, this should appear as a straight line as well. So this is consistent with what the analysis is telling you, that when you have entropic error bound, you're getting faster than any sublinear rate, but potentially slower than linear. And for the logarithmic error bound, our numerical findings were also consistent with the theory. So although we only had a lower bound to an upper bound, applying cyclic projections to this, which is the case where you have a logarithmic error bound, shows that the convergence rate is something like this. And this is a log-log plot. So this suggests that this is lower than any sublinear. If this were sublinear, this should be like straight line. And that is more or less what I wanted to tell you today. That consistent error bound functions can be used to analyze convergence rate. Sometimes a complicated integral might appear, but you can maybe massage this away using regular variation. So thank you very much.
Yeah, thank you so much, Bruno, and thank you very much for the hint about regular variation functions. So, and we have a question from Scott. So, Scott, please ask your question.
Hi, Bruno. Thank you for an interesting talk as always. So you mentioned that you can get a lower bound for the upper bound by using some alternative techniques that don't involve solving this integral, right? If you could solve the integral, would you then be actually able to get the lower bound?
So even if you solve, the problem is that even if you solve the integral, this quantity here, we're talking about estimating this, right? Mm-hmm. So if you solve this exactly, still you only have you only have a upper bound to this. So actually we have some issues, I guess, regarding to the optimality of this. So we don't know in principle whether this bound is tight. So
would you get anything extra from being able to solve the integral? Would that help you advance towards this, or would that be superfluous at this point?
So for example, we were able to show that the convergence rate more or less sits between sublinear and linear. Perhaps solving the integral directly might give even more insight on what exactly is between sublinear and linear, you know. Some concrete shape for that, not only in the asymptotic sense. That would be something that could be gained by precise analysis. Yeah, thank you very much for the question.
Thanks.
Okay, so any more questions from the audience? So, oh, well, maybe I ask a small question. So exactly this slide. So you have M sets, convex sets, and what would be, say, how large M could be so that you still can actually do all these nice manipulations?
So the good thing regarding this is this analysis is not influenced by the number of sets. So the most important thing is when in the analysis everything gets abstract in this max term. So in the proofs it doesn't really matter if this M is 2 or very large. it should work for any value. I thank you very much.
Yeah, thank you. So
I'll ask another one if there's time.
yeah, you can ask definitely, please.
Right. Sorry about that. I got disconnected. The other question I had was, so you've got these results, right, for the negative infinity face, right, the two-dimensional face, or the entropic error bound. Have you done any kind of anything numerically looking at the really bad one, the reciprocal logarithm? I mean, I assume you know it's sublinear, but
so the thing is that it's worse than sublinear.
Yeah.
So it corresponds to this example. So this corresponds to the logarithmic error bound.
Right.
So this is worse than sublinear, and this is consistent with this part here that says that this quantity, this upper bound, is lower bounded by any sublinear stuff.
Mm.
So yeah, so the bad case is very bad. So for the exponential cone, when things are good, they are very good, and when things are bad, they are very bad. That's more or less what's happening.
Cool. Thanks.
Okay, so thank you very much, Bruno. So I can't see any questions from the audience, but I think it's about time to finish. So I would like to thank all the speakers from this session. So we had 4, and all the participants, discussions, tutorials. So thank you very much all. And so this is the end of the session. So I'll stop recording.